Hello everyone, welcome to Tuteetute. In this particular video, we are going to see about total internal reflection. Total internal reflection we are going to see in this video, as I said earlier. For that, just I am taking one interface that is a XY plane. X-axis, Y-axis coming towards you, and Z is the normal to this particular interface or the boundary. And to understand this one, we will incident one electromagnetic wave obliquely on this particular boundary. Okay, so because of the impedance mismatch, medium 1 is having the impedance is eta 1, medium 2 is having the impedance is eta 2. Because these two impedances are different, and due to this mismatching of the impedances, what will happen? Certain power of this incident wave will be reflected back into the medium 1, and remaining power will be transmitted into medium 2. This is what is happening. Okay, so what we need in the sense here in this particular concept, total internal reflection is possible here. Okay, so how it is possible means that depends on how we are obliquely sending. Okay, what is the angle is making this total reflection is possible. That is what we need to understand. Okay, so no signal should enter into medium 2. Everything should be reflected back. That is our concept here. You are incidenting on this boundary. Because of the impedance mismatch, something will be reflected, something will be transmitted. But what I need in this particular concept, total thing should be reflected back. That means nothing should be transmitted. Okay, for that particular purpose, what are the conditions we have? That is what we need to see. Okay, so we know about the Snell's law. First Snell's law is theta r is equal to theta I. Second one, that means angle of reflection and angle of incidence are related by Snell's law of refraction. That is n1 sin theta 1 is equal to, or sin theta I is equal to n2 sin theta t. Okay, n1 n2 are not impedances like eta 1 eta 2. n1 n2 are the refractive indices. Okay, so we can modify this one and we can write in terms of the phase constants beta 1 sin theta I is equal to beta 2 sin theta t. Like this we can able to utilize. Now what I am telling, I am looking for total internal reflection. That means no signal should enter into medium 2. That means I should not have transmitted signal. So when I look for total internal reflection, what I want to say is transmitted signal should be 0. Transmitted signal or the transmitted power should be 0. When there is no transmitted signal, there is no question of theta t. Okay, if there is a transmitted signal, that transmitted electromagnetic wave vector is making angle with respect to normal to the interface, that is theta t. What I am saying is there is no transmitted electromagnetic wave. There is no question of theta t. So theta t should not exist. Okay, theta t should not exist. For this one, I am looking this equation and writing the equation for sin theta t. Sin theta t is equal to what we can write from this one? Beta 1 by beta 2 multiplied with sin theta I. When can I say this theta t is not existing? Sin function value changes from -1 to +1. Okay, the maximum value and the minimum value of the sin function are 1 and -1. So this right side part should be in between -1 and +1 only. Then we can tell theta t is available. But my intention is I should not have theta t. That means this must be greater than 1. If sin theta t is greater than 1, no angle satisfies this particular relation. Okay, is it correct? When I say sin theta t is greater than 1, what is the value of theta t? Not possible. There is no physical angle to satisfy sin theta t is greater than 1. That is what I need in case of the total internal reflection. So now using this incident angle, we can comment about this total internal reflection. Sin theta t is greater than 1. for not having the transmitted signal. Similarly, beta 1 by beta 2 into sin theta I is also greater than 1 for not having the transmitted electromagnetic wave. So, anyhow sin theta I maximum value is 1. So, if you have maximum value also, but beta 1 by beta 2 should be greater than 1 to satisfy the same rule, same condition. So, beta 1 by beta 2, if it is greater than 1, from this we can get beta 1 is greater than beta 2, or from this relation we can tell refractive index of the first medium is greater than the second medium. So what is the meaning of this one? Denser to rarer. Okay, so this total internal reflection is possible from the denser medium to rarer medium only. This is the very important condition we have derived here. Once again I am repeating. In case of total internal reflection, what is the meaning of that one? Whatever the incident wave is there, everything should be reflected back into the same medium 1. So no signal should enter into medium 2. That means there is no transmitted signal. There is no transmitted signal means there is no question of having theta t. So theta t should not be existing means sin theta t should be greater than 1. That means beta 1 by beta 2 sin theta I is greater than 1. If you take its value is maximum or something else also, we can tell beta 1 by beta 2 is greater than 1. That means beta 1 is greater than beta 2. It is indicating that medium 1 must be denser medium, medium 2 must be rarer medium. Then only this is possible, then only it is possible, then only it is possible, then only it is possible. That means for not having the transmitted signal, that means for having the total internal reflection, we need to send the wave from this denser medium to rarer medium. That is the thing. We need to incident the electromagnetic wave on the boundary which is in between denser medium to rarer medium. Then only this total internal reflection is possible. That is what we can tell. Okay. So this is the thing we can able to observe related to eta t. Now, using reflection coefficient expression, something we can able to talk about this reflection coefficient concept towards the total internal reflection. For example, if you take the perpendicular polarized wave reflection coefficient, what is the formula we have? Eta 2 cos theta I minus eta 1 cos theta t by eta 2 cos theta I plus eta 1 cos theta t. Already we know that theta t is not existing for the total internal reflection. So to talk about that one, we need to write that one in terms of the incident wave angle. So for that, whatever the equations we have taken previously, beta 1 sin theta I is equal to beta 2 sin theta t. So sin theta t is equal to beta 1 by beta 2. What we can write here? Sin theta I. This is what we can write. But here we have cos function. So sin square theta t is equal to beta 1 square by beta 2 square sin square theta I. Just I have squared this particular equation. So sin square theta t is equal to, I got this one. Okay. Now just take this cos square theta t. How can I write this one? 1 minus sin square theta t. Why I am writing for cos square theta t? Because here I need cos t. That is why I am converting into cos function. So it is equal to, what we can write? 1 minus, the sin square theta t means this one we can write na. So beta 1 square by beta 2 square into sin square theta I. Like this we can write. Now you see theta t is written in terms of the theta I. Like this we can able to write. So now what we can able to do, because here cos t is there, we can take root. Cos theta t is equal to root of 1 minus beta 1 square by beta 2 square into sin square theta I. But we know one thing, we are looking for, these equations can be valid in general also, but we are looking for total internal reflection. When we take this total internal reflection concept, we have already understood that sin theta t must be greater than 1. That means this must be greater than 1. So this part is greater than 1. Whenever this part is greater than 1, 1 minus the value which is greater than 1 means this is negative number. So root negative means it is actually imaginary. So to indicate that one, just take minus is common here, minus 1. So that is we can able to write j square, root j square means j will come outside. So here we can write beta 1 square by beta 2 square sin square theta I minus 1. Like this we can write. So in case of cos theta t, we can substitute this one. So now I am modifying this particular gamma perpendicular expression using this particular relation. So eta 2 cos theta I minus eta 1 cos theta t, that is j root of beta 1 square by beta 2 square into sin square theta I. Okay, this is just for cos theta t by eta 2 cos theta I plus eta 1 cos theta t. Cos theta t means what we got here, that one I am writing. So j root of beta 1 square by beta 2 square sin square theta I. Why we are doing all these things means we need to get the conclusions on the reflection coefficient. What is the nature of the reflection coefficient? That is what we need here. Okay, so when you take the condition that theta t is not existing, that means sin theta t is greater than 1. That means if you make beta 1 by beta 2 and sin theta I is greater than 1, what will happen? Total internal reflection will be happening. For the total internal reflection, what is the gamma value? Actually, it should be 1. Okay, from your transmission line analysis, when we will be having this particular gamma value 1, gamma is equal to generally ZL minus Z0 by ZL plus Z0. If you take load is open circuit, this is I have written from the transmission line concept. Okay, if your load is open circuit, that means ZL is infinity, then this numerator is very large value, denominator is very large value. This Z0 can be neglected so that you will get 1. If your load is short circuit, then gamma is equal to minus 1 you will get. Plus 1, minus 1 are representing the open circuit and short circuit loads in case of the transmission lines. Okay, so what is the meaning of having reflection coefficient is equal to 1 means whether it is plus 1 or minus 1, total signal will be reflected back. Now we are talking about total internal reflection, both are similar. So to have the total internal reflection, for not having the transmitted wave, what should be the value of gamma? 1. You see here, did we get 1? Are you observing here gamma value is 1? Yes, we can able to tell here gamma value is 1 by taking the magnitude. So don't see the total expression, just to see here eta 2 cos theta I is there. Here also eta 2 cos theta I is there. Here the imaginary part is eta 1 root of this particular thing, beta 1 square by beta 2 square sin square theta I. Here also imaginary part is that one only, but entire numerator can be taken as real part A minus J into imaginary part is B. By denominator is also like that only, na, A plus JB. Now you take the magnitude here. Numerator magnitude is square root of A square plus B square. Denominator magnitude also square root of A square plus B square. That means magnitude of gamma perpendicular is equal to 1 only. So it is true. When you get this gamma magnitude is 1, what is the meaning of that one? ER by EA is equal to 1. ER by EA is equal to 1. From this we can tell ER is equal to EA. Whatever you incident, everything is reflected back. That's why ER is equal to EA. That means there is no ET. ET is equal to 0 now. Okay. So everything has been reflected. So it is true. But we calculated the magnitude. We got 1. So the total is reflected back. Okay. What about phase? Phase value you will get. Okay. What is the phase we will get here? I am writing gamma. Angle of gamma perpendicular is equal to, it is tan inverse of minus B by A. Denominator phase is tan inverse of B by A. By sending to the numerator, we will get minus 2 tan inverse of B by A. So phase will be there. Some phase will be added. So whatever the wave we have incident, that is reflected back completely, but with the change of phase. That is what you need to understand. In case of transmission lines, whatever the wave is transmitted towards the load, if it is open circuit, with the same phase it will be reflected back. But if it is short circuit load, with out of phase it will be reflected back. Now here, if you make the things like this, that means if you take this beta 1 by beta 2 sin theta A is greater than 1. If you take the mediums like that, then you can get total signal is reflected only. Okay, total will be reflected into the same medium, that means medium 1 only. But for the reflected wave, there is a different phase will be there compared to incident wave. Incident wave may have some phase, but for that phase, this phase will be added. That is what we need to remember. So in this particular case, whether it is perpendicular polarization or the parallel polarization, magnitude we can have 1 for the reflection coefficient. That means total signal can be reflected into the medium 1 only, but phase will be added. So in case of the total internal reflection case, gamma, magnitude of gamma is equal to 1, but angle of gamma will be some value. That means some phase will be added to the reflected signal. But magnitude is equal to 1. Magnitude is equal to 1 means what? It is indicating EA is equal to ER only. So whatever the magnitude is there for the incident wave, same magnitude will be there for the reflected wave, but phase will be different. That is what you need to understand. So in case of total internal reflection, this is what is happening. Okay. So conclusions on the reflection coefficient in the total internal reflection means this is the conclusion. What is the conclusion? Magnitude of gamma is equal to 1, but phase of gamma is some value. So the reflected wave will be equally with respect to the incident wave in terms of the magnitude, but phase will be different. Phase of the reflected wave is different from the phase of the incident wave. That is what you need to remember. Conclusions on the reflection coefficient in the normal incidence. Here, what is happening means, if you see the gamma expression, what did we have? Eta 2 minus eta 1 by eta 2 plus eta 1. In case of the normal incidence, already we have seen. So these are real values only. So gamma value will be real value. That means there is no phase. Okay, here there is no concept of the phase. So phase will not be added to the reflection coefficient. So same phase will be there for this incident wave and reflected wave. So if you are using the normal incidence or the whatever the normal reflection is there. Okay, if you take the normal reflection case, the reflected wave phase is not different from the incident wave. That is the very, very important point. Okay, but when you take this total internal reflection, because it is a complex quantity, gamma is a complex quantity here. Gamma is complex quantity in case of the total internal reflection. This is a very, very important point. If you know that it is complex in nature, it is having magnitude because it is totally reflecting back, so that we can able to tell its magnitude is 1, but phase will be there because of the complex nature. But when you take normal reflection, it is real. Gamma is real. Real number means there is no phase. So phase will be same for the reflected and incident wave in case of the normal reflection. So these are very, very important conclusions in order to talk about the polarization of the reflected wave. Okay, that part we are going to see in the next video. Okay, thank you.